Hey, I'm graduate student at Hansa University. It's a really honor to announce my study today to you. The topics I'm addressing today is the implementation of drowsiness detection and the safe driving system for automobile drivers. Due to the development of the road and the traffic industry, overall system automation and intelligence for the functions of the vehicle and the safety management of the passengers are being carried out at a rapid pace. But it is still difficult to completely exclude the accident caused by human factors. According to the analysis of Korea Transportation Industry Research Institute and the Road Traffic Corporation, 25,259 accidents caused by drowsiness driving occurred in last 10 years in Korea. 1,264 deaths occurred and the mortality rate was 5%. That is more than twice that of the whole traffic accident cases and also about 1.8 times higher than the rate of death of drunk driving accident. The vehicle driver surveillance technology to prevent drowsiness is directly related to the advancement of the automobile industry, leading by the United States, Germany, and Japan. The technology that is mainly applied is image processing, utilizing the camera and the surveillance camera sensors that is installed in the car to monitor unnecessary actions that distract attention and give warnings to the drivers. This table shows the driver monitoring system based on the commercialized image processing for domestic and overseas automobile production companies. In this study, we used GY85 embedded sensors to measure drivers' head motions. The accelerometer is capable of measuring gravity acceleration in x, y, and z axis in a range of plus or minus 2 to 16 g with 2 power 10 resolution per unit gravity. The gyroscope measures the angular velocity of the x, y, and z axis also at the sensitivity of the plus or minus 2000 degrees second and then directly converts the data using the ADC with a resolution of 2 power 16 and convert it to actual instantaneous angular velocity. Then the converted value is integrated with the sampling time to obtain pitch, low, and yaw. Magnetometer is used to measure the intensity and the direction of the magnetic field in the case of the space and is used for measuring the azimuth angle in this case. It is ideal for driver to continuously keep looking forward for safe driving, except for the necessary manipulation activities. However, as traveling time becomes longer, the sleepiness due to fatigue, interference with external environments such as the passengers, and the deterioration of concentration may result in the failure to keep track of the direction of the travel. Based on this assumption, the measured range of the sensor generated by the vertical and horizontal head movement is modeled in the form of a cone here. The normal and abnormal range of the vertical and horizontal movement of the headset is determined logically according to the measurement result. The logic diagram here shows the logical algorithm for detecting drowsy driving from the driver's head movement. When the system is initialized and the head position is set, a continuous signal is input every sampling time by the driver's head movement from the sensor based on this. Accordingly, the system converts input data into the change angle and determines whether the input data does not deviate from the set limit angle or not exceed the set limit time. As a result of a judgment, if the deviation is out of the limit, angle and the time in the vertical direction, a drowsy driving warning is generated. In the same manner, if the limit angle and the time in the horizontal direction is exceeded, an inadvertent driving warning is issued. This warning lasts until the condition is cleared. If the condition is cleared, all warning actions terminated and the input signal comparison review mode is returned. In order to determine the drowsy state by recognizing the driver's head angle change, a filter step is required to filter the noise due to the error of the sensor itself or the surrounding influence. In this study, we applied the extended Kalman filter, which shows the most reliable result in the continuously changing external environment and the signal processing through the experiment of our previous research. The headset hardware was made by 3D printers, and we used this to directly reproduce drowsy operation and careless driving situation in the tired state, and verify the performance and the practicality of the designed algorithm and collect the result data. Based on the data collected through the preliminary experiments, we set this limit of angle of change for normal driving operations, reflecting the propensity of the experimenters. The conditions, the drowsy driving state was set when a time period of 3 seconds elapsed in the vertical direction plus or minus 10 degrees relative to the z-axis, or in a state in the horizontal angle was out of the angular range plus or minus 45 degrees with respect to the x-axis. This graph shows the result of about 2 minutes sampling analysis of vertical head movement among the data collected through the headsets. The vertical axis represents the angle and the horizontal axis represents the time in seconds. As predicted from the technical analysis of the sensor, the accelerometer continuously generated the over-limit impulse signal due to the external noise and showed the sensitivity to the small vibration. The gyroscope sensor initially calculated relatively accurate angle change, but it was observed that drift of about 15 degrees occurred for 2 minutes due to accumulation error. That is because the characteristics of calculating angle change by integrating instantaneous angular velocity. We solved this problem by applying extended Kalman filter. The right side of picture of the graph shows an example of the warning signal processing by a filtered sensor output signal. The example duration of an output signal for 20 seconds and 4 times of state, exceeding the limit angle of 10 degrees occurred at this time. There are 3 cases where the limit time and the limit angle are exceeded. Excuse me. In case of those 2 conditions are satisfied through the program logical comparison, it is designed to initialize the warning signal and send commands to the headset to warning drivers. In conclusion, the result of the driver test that reproduce drowsy driving and careless driving conditions show that the drowsiness detection system proposed in this paper has sufficient producibility and practicality. By applying appropriate algorithms and filtering, use low-cost and off-the-shelf parts. Future studies will be carried out to further improve the hardware, reduce the size, and wait for the convenience for the driver wearing and using for long period of time. Thank you very much.